Okay, so just to wrap up what we were doing last session, we're trying to finish off this introduction of the Fourier transform. We had seen how in discrete time the general Fourier transform becomes a discrete time Fourier transform, which is basically just another Fourier transform, but has this periodicity in 2 pi in our frequency variable, which we now denote little omega. And then we said, okay, but if we want to actually do something on a computer, we need something which is a discrete spectrum as well, discrete Fourier transform that is itself discrete. And that gave us the DFT, which is basically, you can think of it as just sampling the spectrum, the frequency axis, on a set of discrete uniformly spaced points, but over the minus pi to pi or 0 to 2 pi range. And if you have an n-point sequence in the time domain, you can represent it as an n-point sequence in the frequency domain, and it's a complete description. It's a nice, one-to-one Fourier transform pair, and we have a discrete Fourier transform which we can use on computers, which all makes sense. And then we were talking about the relationship between the DFT and the DTFT. The DFT is just sampling. The DTFT is the continuous function, right? It's just the Fourier transform evaluated for a sequence that only takes values at specific times, a discrete sequence. And the DFT is just basically reading off some values at some particular points. If you were thinking about this as the problem of like, I've got this continuous function which represents this n-point sequence, which is what the DTFT of a finite length sequence does. And so I need to be able to recover what the n-point sequence was. Under some restrictions, any set of n points and n samples from the spectrum could do it, right? Because that would give you enough information, and then you could solve for the sequence that would give you those samples. So in some sense, the choice of these samples is not that important. But if you have n samples, you should be able to reconstruct. If you have n samples of the spectrum, as long as you didn't hit any pathological cases, you should be able to reconstruct n values of an n-point time domain sequence. But by doing it in this uniform way, then we can have this nice expression here where we just have a single, parameter we have to use, the w sub n, which is just e to the j omega n for the omegas equal 2 pi k on n. And so it all works out nicely. We get a nice a Fourier transform that behaves like the ones we're used to. So that's what we use. And then I talked about how we could basically interpolate. If we have the smooth function, we can just read off the values at these uniform points to get the DFT, the discrete function. And if we have a discrete function, we can basically interpolate. We can figure out the smooth line in between. And in this sort of interpolation regime, there's this idea that you have interpolation kernel functions which sort of tell you how, given particular points, how you spread them out. It's like, I don't know if you've heard of this point spreading function, which astronomers talk about. It's like an impulse response, actually. But it's sort of, that's what's going on here. It's how you spread these individual points to sort of fill in the gaps in between. And so we can see how to do that. That yes, indeed, we can recover exactly the DTFT we started from the DFT, because, of course, we could always just invert the DFT, get the finite length sequence back, and calculate its DTFT. If we can do that, if we can take a continuous DTFT, sample it, and then take its I DFT, we can get a sequence back from a DTFT. And if we take an n-point DFT, if we sample at n points and do the IDFT, we get an n-point time domain sequence out. But what if the original sequence that we took the DTFT of was longer than n points? There's no way you can fit more than n points into n points, so something has to happen. So we work through the math of that, and what happens is you get this folding down, that the n-point sequence is every n-point chunk of the longer sequence sort of superimposed, shifted down by some shift of n, big N samples, and then superimposed. And so in this particular case, we were taking an 8-point sequence and sampling a 4-point DFT and then IDFTing that to get a 4-point sequence out. And what it is the first 4 points of the sequence and then the second 4 points, the sequence shifted down and added on, which you can visualize as this sort of, blocked shift of the original longer sequence until everything sort of appears in this 4-point window, which is the sort of the universe of time samples for a finite length sequence. So we call this process time aliasing. This is the time aliased version of this longer sequence because we forced it to be represented on a 4-point basis. And so this gets to this point about this sort of the different behavior of the time axis in the DFT world. We're used to thinking of time as being something that is unlimited, goes on as far as you want to look. But when we start working in this finite dimensional time space, which is what the DFT is implicitly working with, which either means that you can't have values of n outside of 0 to big N minus 1, or it turns out equivalently, or somewhat equivalently, you can have, if you try and look at points outside that range, just get repetition. So it's this finite length sequence that repeats indefinitely. That sort of time axis has these properties which basically are sort of as if it was a circular time axis. So let's try and get at that by looking at what happens with time shift. So, and this is because we want to figure out how our properties that we've generalized from the Fourier transform to the discrete time Fourier transform, how they actually appear in this DFT, discrete Fourier transform space, because clearly there's going to be some problems. So we're saying that in the discrete Fourier transform, the time axis has to be, it only really exists between 0 and big N minus 1. But in the discrete time Fourier transform, we had a time shift operator, something like if you have a sequence, if you delay it by n0 points, then the Fourier transform is going to be, e to the minus j omega n0 times the Fourier transform of the unshifted sequence. Well, we can't shift a sequence, a finite length sequence by n points and have the points sort of shift off the end because there's an end, there's a hard end, you can't have stuff, this has to go somewhere. And so in the discrete Fourier transform domain, the time shift becomes modulo n. So basically when you push something out of the end here, it reappears at the beginning, right? So if I've got, some set of values n from 0 to 3, and I'm trying to calculate a new sequence which is that delayed by 2. So, h of n is g of n minus 2. Then how do I find my point in the sequence I'm delaying to put it into the first sequence? Well, if I try and evaluate it, but then I find the value I'm trying to get is outside of the range 0 to big N minus 1, I just add or subtract multiples of big N until I get back into the principal range. And so that's what the modulo indexing here does. So this is saying, well, we can subtract any number we want off n, but then after we've done that, we have to use the modulo indexing to move it back into the range 0 to big N minus 1. If we do that, then it does kind of what we expect, right? This is the analog of what it did in the DTF-T domain, that we have the original spectrum, but each term is modified by a linear phase term. W sub n is e to the minus j 2 pi on big N, so that's kind of the same thing. So this is taking the place of omega, and this is n0 again. So it's just a linear phase, right? This twist in the this sort of helical twist of the spectrum as a result of shifting in time winds up the phase of the spectral values, but leaves the magnitudes unchanged because this thing always has a magnitude of 1. So here I'm just explaining again what this angle bracket modulo notation means. It just means that if we've got this for some range of values of n, if n has to be between 0 and big N, and n0 is also between n0 and big N, then as long as this thing remains non-negative, then we just take it as is. But if n is smaller than n0, if we're trying to subtract more than this, depending on which one is larger, right? Either because we're trying to take values of a sequence for the n before n0 happens, or we're trying to evaluate it for a delay that's larger than a particular point, then we add on a big N. And for this range of n0 and n, it's going to work out. But in general, if we try and use even larger delays, we might have to use more, larger multiples of n to make it fall into this range. But we can always do it. So this is like, okay, this is like, a case. It's not very intuitive to think about, well, okay, I have to just figure out whether n0 is before or after n, and then figure out what happens. But this picture makes it much easier to understand. And so this is the idea that the time axis in this finite dimensional time regime, it's like a circle. And so now, here's the modulo delay operator. Here's an initial sequence. If we delay it by 2, right, so that would normally we'd expect that to make the 0th value appear at 2. G of n minus 2 is going to take on the same value here when n is equal to 2. So here's the delayed part. But the bit that would then fall off the end, these 2 points, reappears at the beginning, which is what the expression on the case on the previous page was saying. But if we think about these points on this kind of circular time axis, basically what happened was we had time 0 pointing back here, and then when we delayed it by 2, we moved the time 0 origin pointer to be here, or something. Well, we did it the other way around. We actually moved it back to, so the figure's not good. But, you get different sequences all coming from the same set of points on this circular axis, and just depending on where you start reading it from, right? But you just start at a particular point, and you read through, and you get a sequence out, and that's the delayed sequence. And this is, it's exactly the same as you would if you had a unlimited time axis, except in an unlimited time axis, this would be a flat thing. You'd move the origin around, and you'd read the sequence from there. But here, there's just this connection around the back, where the end of time starts off at the beginning of time again. So one of the relations we deal with is the reversal in time, right? We know that if you flip the time axis, then it's the same as flipping the frequency axis in the DTFT. What does time reversal mean in this modulo n space? Here, and so you might think if you just saw this, n-point sequence, like, oh, I can flip that in time, no problem, just flip it around like this. And that's the wrong answer. What you have to think about is, no, flipping the time axis means flipping around n equals 0. But now we've got, and whereas flipping like this would be flipping around n equal 2, which is something else. So if we want to flip it around n equals 0, but we're saying that n can't go negative for our sequence, okay, let's go back to thinking about this sequence as an infinite duration periodic sequence, right? Because then, okay, now we can allow n to go negative. The sequence is defined for all values of n, it's just that it's periodic. If you had this infinite duration periodic version of the finite dimensional sequence, then when you time reversed it, well, that's obvious what that looks like. It's just the same sequence but reading this way, ramping up this way. And then you say, well, what if I want to represent this reverse sequence as a single period that repeats? What is a single period that repeats? And it's this. And so now, and that's how we define the this is the correct version of time reversal in a finite dimensional sequence. It is in fact just x twiddle of negative n modulo n, which is what we think it should be. But that just doesn't necessarily, it's a little bit of a surprise what that looks like, which is the 0 point stays the same because 0 modulo n is still 0. But the remaining points, 1 through n minus 1, are then time reversed because minus 1 modulo n is actually minus 1 plus n, so it's n minus 1, which is this point, and then, minus n minus 1 modulo n is 1, right? Because minus n plus 1 plus n So you get this set of points. So the math all works out. There's nothing surprising I'm saying here, but it's just like in order to remember that to avoid the natural mistake of thinking that reversing a finite length sequence is just reversing it, this is the picture to think about. That it's and the bottom line is the 0 point stays the same, and then the remaining points get reversed, which is not particularly, it seems very arbitrary until you look at it this way and you see that it fits in. Okay. So one thing we noted is that once you've got this mapping from an n-point sequence to an n-point sequence, from the time domain to the frequency domain through the DFT, then the idea, and that you can think about that, for instance, as a square matrix multiply. Then the IDFT is the same thing. It's just another square matrix multiply, which turns out to be the inverse of that matrix, but it turns out because the symmetry and structure of that matrix, the inverse is very similar. And we can think about, I've mentioned several times this idea that, the sort of the mathematical surprise of the Fourier transform is that there's really no particular difference between the time and the frequency domain. Mathematically, they behave very similarly. And you can quantify that here by saying, well, we've got this idea of relating, Fourier transform and these time-frequency pairs. And so if g of n, its DFT is g of k, then we could think of a sequence in the time domain whose values were these values here. And we could denote that as g of n, right? So it's like, this is confusing because now we're talking about something which was calculated as a frequency domain set of values, but we're thinking about it in the time domain. But if we had a time domain signal that had those values, then its Fourier transform would be something close to the time domain values here. It's not quite the time domain values. Time domain values circularly time reversed and then scaled by n. But it's basically what they're saying is this is, if we want to do an inverse Fourier transform, it's almost the same as the Fourier. This is a forward Fourier transform. This is a forward Fourier transform, and it almost gives us the same sequence back. I recognize that that's kind of confusing to look at here just because of the notation is weird. So let me just, maybe it's easier in MATLAB. So if I define a sequence like this, I can take its Fourier transform like this. And then because we started out with some arbitrary non-conjugate symmetric time sequence here, the Fourier transform has got real imaginary parts, right? So it's a complex Fourier transform, although because this was real, this Fourier transform, just while we're looking at it, is in fact conjugate symmetric, which means that this value, the 0th value in conjugate symmetry is what can be whatever it wants to be, but the first value after that is the conjugate of the last value and stuff like that. So this value is conjugate with this value is conjugate with this value, this value is something like that. But anyway, it's just some set of, it's an 8-point sequence, start out with an 8-point sequence in the time domain, have an 8-point sequence in the frequency domain. That's what DFT does for us. If I then take the DFT of that big X, right, which is the frequency domain representation, if we compare that to X, right, now we notice that we took an FFT, but this time we took an FFT of something that was conjugate symmetric, so we get a pure real sequence out. And more to the point, we're looking for it to be n times the circular time reverse version of the original thing. So the circular time reverse version of this would be 8, and then these ones all flipped around. N is 8. So lo and behold, we get 8 times 8 plus 8 times 1, 8 times 1, 8 times 2, 8 times 2, 8 times 3, 8 times 4, 8 times 5. Right, so just taking the FFT, so FFT of X, of little x, gives us circular time reverse scaled by n x. Okay. Any questions? Okay. So one of the, well, I've emphasized how important convolution is, that it's kind of central to linear systems. And we noted when we were talking about DTFT that, well, one of the useful things about DTFT is that under the Fourier transform, convolution becomes multiplication, which makes it much easier to do algebra and to think about the ways that we can manipulate and combine and reorder sequences, because the algebra all works out in a very familiar way once convolution becomes multiplication. And then we even said you can use it. If you had some way of calculating DTFTs, you could simply multiply them together, put them through an IDTFT, and get an answer. That was mainly useful for closed-form manipulations where the DTFT was some nice, closed-form expression, and then we could calculate algebraically what the result of their convolution was. In the DFT domain, we finally got a Fourier transform which we can actually calculate on a computer. And now we could actually do the thing I was sort of implying we could do with a DTFT, which is to calculate the convolution of two sequences. We could calculate their Fourier transforms and calculate the inverse DFT. That isn't necessarily that great a win because, well, we already know how to calculate the convolution. If you give me two sequences, I can just put them through the convolution equation and get that out. So why would I want to go through all this process of doing it in the Fourier domain? You could imagine situations where you happen to already have these sequences in the Fourier domain, and so it was worth it, or you wanted the answer in the Fourier domain, so by calculating all in the Fourier domain, you could avoid some of this. Amazingly, it turns out that actually because of this particular algorithm, the fast Fourier transform, it works out to be more efficient on a computer to calculate large convolutions by taking Fourier transforms and multiplying them together. But we'll see that later. But all we have to do now is note that, yes, we expect that to be possible. But of course, there is this problem that we know when we convolve an endpoint, if we convolve two sequences together, the output of the convolution will have non-zero points, which sort of it's the spread. We blurred one sequence by the other one. And so the total number of non-zero points will be the sum of the two sequences less one, right? So it's all the times that they overlap when we line them up. So if we have two endpoint sequences in particular, the output will have non-zero. If we have two sequences which are non-zero of endpoints, we convolve them just using regular linear convolution. The output will have 2n minus 1 non-zero points. In the DFT domain, if we have an endpoint sequence, we take its Fourier transform, we get an endpoint DFT, we multiply another one in, we're still going to have an endpoint DFT. We take the IDFT, we're still going to get endpoints out. And so somehow we've got this thing where this convolution, which wants to be 2n minus 1 points, is only being represented by this endpoint sequence. And what happens, we can work it all through. But you can quickly see that, well, if it worked in the DTFT domain, then obviously the product must be the samples of the DTFT of that full convolution. But now we've done this thing of taking a DFT of an overlength sequence, and so what we get is the time aliasing. So what happens is we get this 2n minus 1 point sequence folded down onto endpoints by shifting versions of it out. And so this is when we multiply DFTs together, we do get a convolution, but it's convolution on this circular time axis, on this modulo n time axis, which means that some of the points that in linear time would have landed further in the future end up coming and overlapping the beginning again, that's just an equivalent way of expressing what happened here. It's exactly the same thing. So that's not normally what we're interested in. I mean, maybe there's some space where we do have an intrinsically circular time axis, and that's fine. But most often we're talking about real time or some other real situation where there's an unlimited axis. And so the circular convolution is like, well, that's not really what we want. That's too bad. But if we're careful, we can, so here's the full definition of circular convolution. And here it is, this is actually what we get out, that if we want to calculate the point, the value of the convolution of two finite length sequences at some particular point, we can just have our dummy variable, our summation variable, go from 0 to n minus 1. So this thing is okay, because we're only ever going to access g of m through 0 for n minus 1. But here, h, which is h of n minus m in convolution, we have to make this modulo n so that it stays within the 0 to n minus 1 range. And once we do that, then we get this equivalent, what is equivalently time aliasing. So these two are a DFT pair, right? That this circular convolution here has a DFT, which is just the product of the DFTs of the individual sequences. And we have a little symbol for it here. We were using an asterisk with a circle around for regular convolution. And so here we're using an n to indicate the point size, like 4 or 16 or something, with a circle around it to indicate circular convolution. There are several different conventions for this, but that's the one that's used in Mitra. Yeah?
So if we had two 8-point sequences and now we would put a star in between,
Yeah.
would it mean something different?
Yes. So if we had two 8-point sequences, right, we could just do regular convolution on them, which would be g of n convolved with a star in the middle by h of n, and that would give us a 15-point sequence out, right? Because the 8-point sequences would line up. But if we have two 8-point sequences and we put a circle with an 8 in the middle here, then we get an 8-point sequence out, which is the circular convolution, which is, it turns out, the time-aliased version of the 15-point convolution. Yeah?
Is there any technique to avoid aliasing, for example, other than zero fading the signal and to make like a regular convolution? Is there any other way?
Is there any way to avoid the circular aliasing? Yes. We zero pad the signal, which I'm about to talk about. Is there any way other than zero padding the signal? I don't think so. I'm not sure. I mean, zero padding the signal is going to be fine. So that's the answer. Let's just that's 3 slides on. Okay. So let's just check that we've got that we understand the circular convolution process with these two 4-point sequences here. So g of n is 1, 2, 0, 1. H of n is 2, 2, 1, 0. Here are the plots of those two. Here's our circular convolution expression. And, we had a couple of ways of thinking about convolution. This is the one where we're taking a weighted sum of time-shifted versions of one of the sequences. But here, and so I'm shifting h by every possible value of m, multiplying that shifted version by the value of g at that particular shift, g of m for m equals 0 through 3. But now when I do the shifting of h, it's circular time shifting. So here's h delayed by 0 points. Here's h delayed by 1 point, shifted down, but this part comes through. H delayed by 2 points. More of it comes around. H delayed by 3 points is the same as advancing it by 1 point in a circular basis. So here are 4 versions of delayed h. Here are 4 scaling factors, which are the samples of g. And then we sum them all up. So the 4-point convolution here is this, which is 2, 0, 1, 2. That's not right. 2, 0, 1, 2. How did that? What? It's 2, 2, 1, 0. What happened? Oh, I've got. Wait, right. I've got to apply these scaling factors. So it's 2 times 1 plus 0 times 2 plus 1 times 0 plus 2 times 1, which is 2 plus 2, which is 4. Then it's 2 times 1 plus 2 times 2 plus 0 times 1 plus 1, which is 7, 5, 4. So we get this convolution out here. And if we wanted to actually calculate the 7-point full convolution of these two, which I think we did before, then when we fold them down, we get this same sequence out. Oh, here we are. So here's the full 7-point convolution without the circular time axis. And then when we do the time aliasing, these 3 points get added on back here, and we get 4754, the same answer coming out. Yeah?
We have the convolution. Is there a way of actually knowing what number is folded when you only have the...
If you have the convolution, if you had this, how would you know which numbers to fold down? Yeah, it's just so there are several different ways you could do it, but basically, if what this amounts to is having some sequence and then representing it, if you like, taking its DTFT, sampling it at n points, and then reconstructing the IDFT, and that will always chunk it on blocks of n, starting at 0. So here, because we're using this thing is the IDFT of a 4-point DFT, right, which is the product of these two 4-point DFTs. So the IDFT of a 4-point DFT is just going to be the blocks of 4 alias.
What I mean is, if you have that, will you be able to guess what the numbers were? Like,
oh, right. So, okay. So, if knowing this, can we reconstruct this? No, we can't. Right. This is that's the problem. That if I've got basically here in general, I've got 7 values I need to find, 7 degrees of freedom, and here I've only got 4 values I know, 4 degrees of freedom. So it's sort of like, so we could set up a bunch of equations that say, well, here's how each of these numbers depend on each of these numbers. But basically, we'd have 4 equations and 7 unknowns. So, without something else, we're not going to figure it out. Now, of course, there's always the opportunity for something else. It might be like, well, I've only got these 4 values, but I know this thing was going to be a sinusoid or something like that. Then there might be a solution or some other constraint. I know there's only a finite set of possible signals here. You could find one that matches. But without any other constraints, you can't generate 7 independent numbers from 4 independent numbers. That's basically it. Okay. So just to summarize the properties of the discrete Fourier transform, the DFT, which all mirror the properties of the DTFT and the Fourier transform. Convolution was a big one, but here it's circular convolution. So if you convolve 2 sequences in the time domain using the circular indexing, then it's the same. The Fourier transform is the product of the 2 Fourier transforms. And lo and behold, there's the converse of that, the dual of that. If you multiply 2 sequences together in the time domain, then it's the same as doing circular convolution on their spectra. Right? Remember that? We had that in the DTFT, but it looked kind of weird in the DTFT because it was an integral, because the spectra are continuous functions, and because the dependent variable here, the integration variable, was in an exponent, so it looked kind of weird. Here this is the same, right? It's the same looking convolution, and the only difference here is the 1 over n. I hope that's right. Anyway, that's sometimes you get a conjugate showing up here, but I guess we didn't here. Duality was this thing that, like, if you have a time domain sequence which is actually the frequency domain sequence for some other sequence, then its spectrum is the other sequence that it was the time domain, that it was the frequency domain version of, with this time reversal and scaling. Parsifal's relation, right, that the total energy, the sum of the magnitude squared in the time domain is equal to the sum of the magnitude squared, or the integral of magnitude squared in the frequency domain. That still works here, but now, again, it's very, very symmetric. They're both endpoint sequences. We just sum up the magnitude squareds. They're the same, except for this 1 over n. Loop gain. What I mean by loop gain is that when you go around the DFT, IDFT loop, you have to include this 1 on n somewhere in there. Okay. So that's, this is basically exactly what we'd expect, the only twist being this circular axis. Okay, so here's this question, right? So I said, that's great, we can do convolution in the DFT domain, but it's not the convolution we were expecting because it has to respect this circular time axis. Given this idea that actually, if we could use this convolution, there's this very fast and efficient way of doing it, what can we do? And the trick is to we're going to get this time aliasing. We're going to get the chunk off the end folded back and superimposed on the beginning, as it were. So the trick is simply just to arrange to make sure that part that gets folded back is always 0. And we can do that by adding zeros to one of our input sequences, or one or both of our input sequences, or equivalently by using a DFT which is longer than the sequence, which is the same as saying, well, we're just going to add zeros to make it a longer sequence that happens to have a lot of zeros at the end, and using a DFT of that. So what we want to achieve is that we know that we can get n independent, unique values out from our final IDFT if we make sure that the DFTs that we're taking are of sequences such that the number of points in the convolution, which is always the length minus 1, as long as that can fit within this n point size, then we're going to be okay. And so the trick is simply to add zeros until we get to an n that can do that as efficiently as we can. So if we've got an L point sequence and an M point sequence, we're going to get an output which is the result of our linear convolution is going to be L plus n minus 1 points. We have to use n at least as big as that, which means that n is going to be bigger than L and M. So we have our L point sequence. We pad it with m minus 1 zeros to get an n point sequence. We have our second m point sequence, and we pad that with L minus 1 zeros to get it to be big n points long. We calculate the DFTs, the n-point DFTs of both of these, which now give us n-point spectra. We multiply them together point-wise to get the DFT of our output, and then we take the IDFT of that. It's going to be the circular time aliased version of this sequence, but this sequence, when we calculate its actual linear convolution, it would be this. It would be this nice sequence out here that ends there and then would be 0 here and 0 here. The IDFT gives us an n-point sequence which you can think of as periodic. So it's as if we're getting this result, which then repeats here periodically. But if we just look at these points, then it's the result of the convolution that we want. So, we said that maybe there's an efficient way to calculate the DFT, and so maybe this is actually a cost-effective way of doing it. Suddenly, we're now using larger DFTs, right? We're having to calculate DFTs of these sequences that involve a lot of zeros. That's not so efficient, right? Now we're adding more computation over simply calculating the DFT of this L-point sequence, in general. But the payback is we get something that's actually useful at the end, and it turns out that even with this zero padding going via the frequency domain, if we use the fast Fourier transform, can be more efficient than directly just calculating the linear convolution in time. Is that clear? Yeah.
So what's the difference between zero padding circular convolution and UFA convolution of two sequences?
What's the difference between zero padding like this and direct convolution of the two sequences? There's no difference. I mean, I'm not quite sure if that's the question you're asking. But obviously, if I have h of n, I can think of h of n as being defined for all n, and then just 0 for a lot of values of n. Or I can think of h of n as being only defined for a certain number of values of n, and sort of undefined outside of that range. But and if I have two sequences like that, which are finite length, I can calculate linear convolution of those two finite length sequences. That's what MATLAB does. You give it a vector of 3 points, a vector of 5 points. You ask for the convolution. You get 3 plus 5 minus 1, 7 points out. But that's neither of the things we've spoken about. That's some other kind of finite dimensional thing. What it gives you is it figures out, it calculates the the convolution, the inner product between time reverse shifted versions, and it only calculates it for the non-zero, for the overlap, right? The region of overlap. And that's actually what that gives you is, assuming these two sequences were infinite length sequences with a finite set of non-zero points in the middle that started at 0, say, then this would be the finite number of non-zero values you get out of the convolution, which would also start at 0. But if you think of them as periodic sequences, then, well, if you had sequences that were finite length but were different lengths, then you can't do circular convolution on them because there's not a single n. If they're different lengths but they're finite dimensional, then they have different n's, right? So you'd sort of have to, in order to do circular convolution, they sort of have to be the same length. And so you sort of have to pad one of them with zeros to make it the same length. But then if you did that convolution, you get something different from what MATLAB calc gives you. You get the circular convolution with the time aliasing, the endpoint thing coming out. And so this zero padded up to the length of the length of the unique points in the linear convolution. That's kind of the way that makes sense to do this. So that's the only interpretation of convolve. That's the most neutral interpretation of what it means to convolve to finite length sequences of different lengths. Okay. Yeah.
Just curious, is there a situation that you actually want the aliased output?
There could be. Is there a situation where the aliased output is something that you'd want rather than something you wouldn't want? So is circular convolution never what you want? No. There are situations where you do want circular convolution. We had this. It was really amazing because I didn't expect to ever find one. But we're doing this work with musical scales, right? And it turns out that we're trying to match two chords that are played on different instruments. And there's this octave equivalence in music. If you play a middle C and you play an octave above it, they're different, but they have a very close similarity. That perceptually, they musically have similar function. And so if I'm trying to match two chords, that if they were played in different octaves, I don't care, right? So I sort of want to fold that back together. And then I was calculating the similarity between two chords by correlating them, which I can get by convolving them, time reversing and convolving. And then I can get this octave equivalence for free just by doing it as a 12-point DFT and then having the aliasing fold down. So that was that's nice. But so if you have a problem where the axis is intrinsically circular, which is true for chroma, for musical chroma, then this is exactly what you wanted. Okay, so that's great if we have two finite length sequences and we want to calculate them, calculate their linear convolution, but using the DFT, using circular convolution, we can pad them out. Of course, this is not such a common case. Very often we have, maybe we have a fixed impulse response of some system we want to implement, but we might have a indefinite, we want to be able to run it for as much input as we get. If we have an input, often we can't control the length of the input. So we could, if we had or even if it might be just the input is really long, if we have two sequences, one of which is, 1,000,000 points and one of which is 10 points, then to do this kind of thing, we'd have to pad the 10-point sequence with 1,000,000 zeros and then calculate the DFTs, and calculating 1,000,000-point DFT is still quite an expensive proposition. Instead, we can basically use linearity, break up the long sequence into a set of short bits, calculate the convolution for each of those short bits, and then because convolution is linear, we can add up all those individual outputs and get the right answer, get the full answer. And so if we have a very long G of M, we break it up into fixed-size chunks, calculate the convolution individually, and overlap. This allows us to use a DFT of some size of our choice. We still have to cover the length of the impulse response, but we could actually do it both ways. So we can use an arbitrarily small DFT if we're worried about memory or something. Also, it means that we can limit the processing delay. If we to calculate DFT, you have to see an entire sequence. But if we can calculate just the DFT of the first chunk and then calculate that part, then it turns out that gives us enough information that we can output the first part of the output of the result, assuming we've got a well-behaved impulse response. and we can go on from there. So we can limit the processing delay. So we can build something which is actually using the Fourier transform to do convolution in real time, which normally wouldn't work, but with some delay, with some sort of fixed look ahead, if you like. So mathematically, if we're saying that g of I is defined as the ith chunk of g, so it's g of n if n is in the range of I to I plus 1 times n, but 0 otherwise. So it's a finite length sequence, but it's a finite length sequence at some particular offset from 0, right? It's a finite length sequence starting at I times n. Then clearly we can get g of n back just by summing up all these sequences. Only one of the sequences will be non-zero at any time, but if we sum them all up, we get all the points back. And then bilinearity, h of n convolved with g of n is just the sum, h of n convolved with the sum of these things, which is the sum of h of n convolved with each of these things individually. Now, these things are not all going to be, they may overlap, because the h of n will spread out this g of n, will blur it out, so there'll be some non-zero regions where they are both non-zero, but we can do that. And so this approach is called overlap add processing, overlap add convolution. And so here it is illustrated graphically. Here's our very long g of n. Here's our finite length impulse response h of n. Then here are our subsequences, gi of n for I equals 0, 1, 2. So it's the first n points, first L points, second L points, third L points. So we're taking L point sequences here. We've got an n point impulse response here, and we're going to use the 0 padding to get the linear convolution out from the DFT. So we're going to pad both of these things out to n points, take the two n point DFTs, or whatever, calculate them. We get now our n point convolution of the two. So you can see this nice little L point sequence gets spread out to be L plus n minus 1 points long. That's okay. This is the result of G0 convolved with H, G1 convolved with H starts at time L, G2 convolved with H. And then we just sum up all of these, and we get the result of G convolved with H. Now, to get the valid region, we have to know that, well, did we get all the points that were involved? And so for this first point back here, if we'd had a g minus 1 of n, its convolution would have had some points coming out here, which we haven't written down here. So these points are not valid unless we know that g started at 0, that g was 0 back here. But once we've sort of gotten past the first m points, which is as far as this sort of tail the previous thing could have spread, then we've got valid points. And as long as we know that we've got each of these chunks involved summed up, then we've got the full convolution. And so here's the to get this point out, we had to have read in all of these points, so we can calculate g of 0, calculate its Fourier transform, calculate its inverse Fourier transform. So we get this sort of set of points out only after we've had that many points in. So that's where the delay comes from. But we can bound that delay by choosing our transform sizes appropriately. Any questions about that? So this is actually, this overlap add processing. It's a very pragmatic thing. It's not theoretically deep. We're just using the identities of convolution and linearity to do this thing. But it does give us an algorithm, which gives us a process which is very useful and has lots of practical occurrences. Yeah?
Is there any restriction for, say, L, like what L is?
What is the restriction on L? You mean how large these chunks can be? Typically, that will depend on, that will be something about the hardware. So that there'll be a size of DFT that well, there are a couple of things. Firstly, the larger the block is, the more gain you get out of this frequency domain processing, because we'll see later on. But basically, it's a gain which is proportional to the log of the length of the block we can use. However, it also, L gives us the space, how much memory we need to use in terms to calculate this. Now, if we've got, typically on a processor architecture, there'll be some memory which is very fast, and then if our working set goes above that, we go beyond the cache and we have to access slower memory. And so there'll be some size of DFT which is efficient, and then as DFTs get larger, then they get drastically slower. So typically you want to, take that into account if you're just trying to make something that's very efficient. And the third thing is that this issue of delay, that the longer the L here is, the more delay there is. And so if you're actually trying to build something which is operating in real time, because the whole reason we're doing this is because we don't really know when G of n is going to end particularly, then typically there'll be some practical limit on how much delay you can deal with. There are some really clever schemes where you break up your impulse response into various pieces. And so you have a short bit of impulse response which can give you the first part of the output with low delay, and then the longer parts of the impulse response you can delay further on. But in general, that's the consideration. It's the processing delay versus the processing efficiency.
Okay, thank you.
Great. Okay, I thought we had, just a couple of minutes to finish on this, but I guess there was a little bit more involved than I realized. But that is it for the Fourier transform stuff. So any questions before we move on? Okay, so we have like 20 minutes left, and I want to get started on the Z-transform. The Z-transform is kind of the pinnacle of our theoretical analysis, right? That we're sort of, the beginning of the semester is building up these theoretical tools, and then the rest of the semester is kind of rolling down, figuring out how we use them and how they can help us with using signal processing. So the Z-transform, and basically we're going to spend the next two classes talking about the Z-transform and how to invert it. So how many people have seen the Z-transform before? Okay, all right, that's not so many. And it's this thing, it's kind of this, it has this reputation as being, particularly amongst practically minded engineers, as being this kind of strange theoretical construct which, is far removed from the kind of practical thing you can understand that you can hold in your hands. The reason that we go into this piece of, elegant mathematics is because it gives us this tool for designing systems. This is the domain in which we want to design systems. But for me, it's more than that. It's like it suddenly explains what's going on in the Fourier transform. There are some things you observe, intuitively about what happens with the Fourier transform. And then when you have this way of thinking about them as emerging from the Z-transform, they become very obvious. And so it's a strange, it's one of these mathematical things where you take this leap, make something more complicated, and then it gives you a way of seeing it that makes it more simple. So that's just to say, stay with me, because there is a payoff. So mathematically, it's not that complicated. It's basically just generalizing the DTFT, but instead of defining DTFT with sum of g of n e to the minus j omega n, we just replace e to the j omega with z. And so the g of z, remember we had g of e to the j omega before, so now it's g of z, which we can write as script z of this sequence g of n. It's defined as the sum over all points in the sequence of g of n times z to the minus n, which looks kind of neat, but we're thinking of this as a function of z. We're not specifying z, right? And so basically z, and moreover, we're thinking about z as a complex variable. That's why we're using z, I guess, if that's a convention. And so this is, which means that, g of z exists on a complex plane. It's not just on the number line, it's sort of any values on this 2D plane. If z is equal to e to the j omega, then it's just the DTFT, right? That's why we wrote g of e to the j omega, because now suddenly we don't even have to distinguish between those two. It's just g of z for z equal e to j omega. But the reason that we're introducing this is because we can think of other values of z. Z of eta j omega is a circle on the z-plane, right? It's just the complex values of modulo of magnitude 1. We could have z equal to r e to the j omega, which would be a set of points on a circle of radius r on the z-plane, on the complex plane. In that case, the g of z would be the sum of g of n r e to the j omega all to the minus n, which would be g of n r to the minus n e to the minus j omega n. This is actually just the DTFT of a different sequence, g of n r to the minus n. And that's kind of interesting because basically we're taking our sequence g of n and then we're sort of scaling it by this new sequence, this exponential sequence. Maybe if r is smaller than 1, we're tapering it by a decaying exponential sequence. And what this means is there will be some sequences where g of n is unbounded, but r to the minus n, g of n, might be bounded. And so we could actually calculate, we could get a value for g of z for some values of z where we couldn't get a value of g of e to the j omega because we had some g of n that became infinite or became unbounded for sufficiently large values of n. So that's something that's a difference, although it's not at the moment a tremendously important difference. But that's interesting because we're saying, well, that's weird because for this in that picture, right, there was some g of n for some values of z. It was unbounded, and for other values of z, it was bounded. So if we think about it as g of z as a function defined over the entire z-plane, we're saying there are some points here where it behaved well and some points where it blew up and didn't behave well. And that's this idea of the region of convergence, that for a particular sequence, x of n, or g of n, if we've got its z transform, g of z, then there will be, in many cases, there will be some values of z for which it is converges, for which we can calculate it and we can get a right value, we can get a stable value. And there'll be some values of z where it doesn't converge, where we calculate it, we get an infinite or a very large value, and moreover, more problematically, the actual value we get depends on how far we get. We can't calculate all infinite values, and it doesn't converge. And so one way we can think about that is this notion of a region of convergence where we draw the z-plane and we shade in the values of z for which this particular function converges. The values of z where if we calculate this sum out, we're going to get a converged value. And so this is also a big source of confusion, and I think that I'd learned it well when I was in school, but it was only a couple of years ago that I kind of really grappled with whether it really means something, which I now want to show to you. Hopefully, you'll get the same experience. So let's just work through an example for a particular sequence to see what happens. So here's a sequence. X of n is equal to lambda to the n mu of n. In the previous example, we'd used alpha to the n. It doesn't matter. We're using some basis. We're raising it to the nth power. We're using the mu function, the step function, to make it right-sided. And so here's an example of what that sequence might look like. Now, this is a diverging exponential. So this is lambda equal to 1.2 or something. Positive real number with a magnitude larger than 1, so it gets larger, it diverges. But in general, we could have some other versions of that. We could even have complex lambda, but it doesn't matter. Now, we've said that x of z, by definition, is the sum of x of n, sum over all n of x of n z to the minus n. So if the x of n is this, then it's only the sum of n equals 0 to infinity, because that's what the mu n does. And then x of n is lambda to the n, z of minus n. So that's our expression for the g of z. And then we recognize this as an infinite geometric sum. And we know there's a closed form for this, which is 1 over 1 minus, if this is sum of alpha, sum of n equals 0 to infinity of alpha to the n, then it's 1 over 1 minus alpha. Here it's sum of n equals 0 to infinity of lambda z to the minus 1 to the n. So the closed form expression is 1 over 1 minus lambda z to minus 1. But we also know that that whole argument, that whole proof of the derivation of the geometric sequence relied on the magnitude of this thing, the thing that's being summed, as being smaller than 1. So we have this closed form expression, but it's only valid when lambda z lambda z to minus 1 is smaller than 1, because if that wasn't the case, then the higher order terms would keep getting larger and larger, and it wouldn't converge, right? So now we have this function which we can talk about, and we can talk about, yes, there are values of z for which it converges, the values of z that give us lambda z to minus 1 smaller than 1, and values of z for which it doesn't converge, for which it gives, it blows up, gives you very large, unstable values. And they're the ones where z is larger. And that's the picture we had on this slide of here, because it's z to the minus 1 that we're worried about. When z gets small, z to the minus 1 gets large, and so the magnitude of lambda z to the minus 1 becomes larger than 1, and we get non-convergence. But as long as z is large enough, then lambda z to the minus 1 will have magnitude smaller than 1, and the whole thing will converge. If lambda itself, so the actual sequence, is smaller than 1, then we have a nice decaying sequence with finite energy. It's something where when we calculate the Fourier transform, we get a nice result. Basically, when we looked at the Fourier transform, the constraint was only on lambda, whether this thing was going to converge, because it was lambda e to the j omega n. So if lambda smaller than 1, when we got a finite energy sequence, we're fine. Lambda larger than 1, we got this kind of sequence, and then we would have said, well, we can't calculate the DTFT. It doesn't meet our conditions for calculating the DTFT. But here it's like, no, it's fine. We can calculate the Z transform. It's just that it only converges for values of Z larger than 1.2, right? It only converges for values of Z such that the magnitude of lambda divided by Z, or lambda Z to minus 1, is smaller than 1. So, and it's basically because both the divergent and the convergent forms of the sequence, they have regions of convergence in the Z transform. There are some values of Z where it converges. It's just they're not. One of them includes the unit circle, the values of Z which correspond to the DTFT. But like I say, this was very much an axiom for me, something that just was true and you had to deal with. But I wanted to try and make it a little more meaningful. So what I did was a little more intuitive and something to put your hands on. So there's this page that's linked to the MATLAB part of the right. If we go to the website, go to the MATLAB scripts, and then down here, there's this evaluating the Z transform numerically. So we're talking about the Z transform. Here it is again. I'm sorry, the tech looks so weird here. And what I'm going to do is I'm going to think about a sequence like this, mu of n times alpha to the n. But I'm only going to calculate it for 1,000 points, right? So in theory, it goes on forever. But I calculate it for 1,000 points. So here's n equals 0.999, alpha equals 0 to the 0.8, x equals alpha to the n, right? So it's alpha to the n for 0.999. By the end of that sequence, the value of x of 999, x of 1,000, I guess, is 1.5 times 10 to the minus 97. So it's almost gotten to the limit of what the smallest number you can represent. This is very, very close to 0. That's what convergence means, right? If we calculate the sum of this, let's just do this in MATLAB. So if I've got x equals alpha to the n, which is some sequence, and I want to know what its sum is, and I want to know what its sum is for all possible values, I can calculate it for 1,000 values, I get 5. I can calculate it for 10,000 values, like this. X, I can still do it. Length of x is now 10,000. But if I calculate the sum, it's still 5, because all the values I've added, the 9,000 values I've added in the second version, are all smaller than 1 e minus 97. so it doesn't make any difference. So that's, this is a converging sum because as I sum more and more points in, the sum doesn't really change very much, and so I get a similar thing coming out. Yeah. Okay, so that's fine. So now we've got this sort of first 1,000 points of the sequence. We can try and calculate our Z transform, more or less explicitly. So the Z transform is the sum of x times z to the minus n, right? And so that's MATLAB speak for that. Sum of x. Dot times means x is a vector of values. Dot times means pointwise multiplication of two vectors. Z dot exponent to the minus n is this scalar value z, or this, scalar value raised to a vector of time points, which is also going to be a 1,000-point sequence. And so I can work that out. And in this case, it's because z is 1, z to the minus n is also 1 for all n. And so this is just sum of x, which we already saw was 5. Which I go on to say here is also because this would be, if z is 1, that's ether j omega for omega equals 0. This is also the DTFT of x at omega equals 0, which is also the 0th bin of the FFT. But that's an aside. So basically all we're saying is we're actually numerically calculating g of z by directly evaluating that sum, although we're only doing it for 1,000 points rather than an infinite number of points. But now we can calculate that same thing, that x of z, for all the other values of z. And so what I'm going to do is I'm going to set up a grid of values of z, and I'm going to do that summation for every possible one of those values. So here's my set of values for z. I'm going to take values of z between minus 1.3 and 1.3 every 0.01. So this is like 261 values. And I'm going to do that for both the real axis and the imaginary axis. So I've got two for loops here, which are basically rho and col, but they could be real and imag. And I'm calculating a value for each one of, for the inner part of these two loops. I'm calculating z as a real part, which is the z-val for the column, because the real axis is the x, which is the column of some big square thing. And then also square root of minus 1, j, times the z value for the row. So now, as I go down different rows, I'm getting different imaginary values. That's my z. And then I'm going to store in big X of row col just this thing. Again, the finite length approximation to the z transforms, the sum of x pointwise multiplied by z raised to the exponents of the times. So that's literally just calculating g of z as written. And then we had this closed form expression that was going to be 1 minus alpha, 1 over 1 minus alpha to z to the minus 1. We can calculate that while we're here, just so we have a comparison. And then we can look at this. Now, it turns out this is like calculating 260 times 260, 1,000-point summation. So it's quite a lot of multiplications. It takes about 20 seconds to run on my computer. I already did it. So let's, if we just, so now if we look at size of x, right? X is the thing I just calculated. Nope. Oh, man, I'm going to have to calculate it again. Sorry. Okay. So now we get to see how long it takes. It doesn't seem like it's that many multiplications, but somehow it is quite a lot of multiplications we're doing. So it takes a while. But then what we're going to get out is this matrix of values, which is basically, we've tried to evaluate the z transform for every point on a grid of this complex plane. So now I can do something like image SC of x. Well, turns out x is complex because the z's were complex, so we can't do that. We can do image SC of abs of x, right, the actual magnitude of it. And this does not look so great, but right, there's something here, but it's not very clear. Now, what's happened is if we look at max of abs of x, and I ravel them so we get all the points. The maximum value here is inf, because, numerically I got down to some nasty values. And MATLAB is trying to auto-scale. I'm not actually sure what it does with that, but so if I look at, here's my plot. If I look at my c-axis, it's actually drawing values between 0 and 1 to 211, to the 1 with 211 zeros after it. So that's not so great. If I restrict the color axis to 0 to 10, then I get something more interesting happening here. Color bar. So here's my entire z-plane. This should be like minus 1.3 to 1.3 here. And then here's my range of values between 0 and 10. There's something going on here. Here is this range which is sort of clipped. And then here is this range which is actually where it went infinite. And so it's plotted at blue. The distinction between these two is not significant. But the distinction in these two is. So what's really going on here? And I can try and use some of the 3D plotting here to try and get to that. I don't know if I do it a little better in the script. Not rendering, yes, it doesn't like that. So if I call AX equal to abs x, and then if I say AX, if I set all the values that are like greater than 100 to a 100, how about that? Okay, great. And so this is, and then if I do shading flat, this is now what it's plotting. So it's saying, yeah, there's some values, and then inside this circle here, I didn't tell it anything about a circle, but it said, oh, there's a circle here, and suddenly, once you get inside that circle, it explodes. And here's the little red ring we saw, and then the blue ring in the middle is the values where it actually went NaN, and so it didn't plot anything. But here, the range here is from 0 to 100, because that's what I clipped these larger values at. But actually, if I limit them down a little bit here, then you can see here's this little thing that we saw. When we're looking above, it looked kind of like this. Here's the part that's sticking up. But here, what's happened here is I was walking along. I had my for loop. I was walking along, calculating the summation. It was giving me some nice value. I crossed this boundary here, and suddenly the summation gave me a large value, an unbounded value. That's what the region of convergence means. It means that, yeah, for this nice, limited, this fairly well-behaved function, just summation over a bunch of values, for a smooth, continuous variation in the input parameter z, we go from convergence to non-convergence in one step. And that's exactly what we're saying. And so this is, but rather than just having some arbitrary circle drawn on a z diagram, this is like, oh, I calculated this numerically, and I got the same thing coming out. Now, it turns out that we can actually figure out this part where there's interesting stuff happening, but it's still converging. That, we can calculate a closed form expression for that, which is well behaved. But the closed form expression is only valid for the part of that that's in the region of convergence. We can calculate that closed form expression inside the region of convergence, but it's no longer equal to summation. It's just, the expression is only valid outside that region. And that's this point here, right? That this summation is equal to this nice closed form expression for points outside the circle, right? For when z to the minus 1 is times lambda is smaller than 1. But it just doesn't hold. It's not related to what this summation is when this doesn't, when that condition is not met. And so we have to get clear in our minds the distinction between the z transform, which is this, and the closed form expression for the z transform, which is equal over the region of convergence only. All right. Well, any questions about that? Okay. We will return to this on Monday.